Thank you very much, Gosha. That was awesome. I have the honor now of introducing tonight's keynote speaker, Rohan. Dr. Nick Suntzeff is an observational astronomer and a cosmologist. The Mitchell Heath Munnerlin Chair of Observational Astronomy in the Department of Physics and Astronomy at Texas A&M University. He received his bachelor's degree in math from Stanford, and then a PhD in astronomy and astrophysics from UC Santa Cruz and Lake Observatories. It's a very storied and prestigious career. I just have some highlights on it to share. He postdocs at the University of Washington. He was a Carnegie Las Campanas Fellow at Mount Wilson, Las Campanas Observatories. He worked down at Cerro Tololo for 20 years, becoming NOAO's Director of Science. He co-founded both the High Z Supernova team and the Calan Tololo Supernova Survey, both of which use distant supernovae to try to precisely measure cosmological constants for accelerating expansion of the universe and so forth. The sampling of the honors and accolades he individually or with his research teams have received over the years. The Robert J. Trumpler Award for his PhD thesis, Science's Breakthrough of the Year in 1998, the Gruber Cosmology Prize in 2007. He was a Jefferson Senior Science Fellowship recipient in 2010 to work as a humanitarian affairs officer for the Department of State. He had the Breakthrough Prize in Fundamental Physics in 2015. And again, another thing I have to thank SSP for is that's how I met Dr. Suntzeff. He's come to Tech many summers since I've been here to give guest lectures for us. And I think maybe in no small part to the fact that Dr. Suntzeff was a TA for SSP back when he was a student. We're very honored to have Dr. Nick Suntzeff here tonight as our keynote speaker. And his talk, as you can see today, is titled "The Day with No Yesterday." So if you please come up.
Thank you for such a wonderful introduction. This is really the high point of my year. I love coming here and meeting all the students. SSP has been a really important part of my life for, well, let me get my clicker over here. This is my 46th year related to the SSP. This is actually me 46 years ago as a teaching assistant here at the Ojai campus. This picture is so old that I'm pointing to only 2 leptons out of the 3 leptons that we're now known. Yes, I used to have my homework. Anyway, so 46 years, the students that I met back in the times that I was TA, many of them are still my friends. It's amazing what these students have gone on to do. Some are astronomers, some of them are actually my colleagues. We had one astronomer in Texas A&M who was an alumnus of this program, and many astronomers, physicists, doctors, entrepreneurs. You people are going to go out and do incredible things in the world. You don't know what you're going to do right now, but you're going to do incredible things. And so over my years, I've kept in touch with many of the students. To me, it's just amazing the accomplishments that this program has achieved. So going back to this, the day with no yesterday. So I'm a cosmologist. When I got out of graduate school, the only thing I wanted to do was to measure how big the universe was, how old it was, and to measure the one missing number in cosmology, which was called Q0, which was the deceleration of the universe. Because with the deceleration of the universe, we could measure how old the universe was and what its future was going to be. We know what the expansion of the universe was, the speed at which the universe was expanding, but we had no idea how fast the universe was slowing down over time. So the second number was the number that I really wanted to measure. And after 20 years of beating at it, we actually finally measured it in 1998. It's called the cosmological constant. It's a big surprise. It's completely unexplained at this point, but it makes up 70% of the mass and energy of the whole universe. So it's kind of cool when you can say you discovered 70% of the universe. The reason why it's today with no yesterday is because the person who invented the Big Bang Theory, we didn't call it the Big Bang Theory, was a very, very interesting person, Father George Lemaitre, cosmologist that none of you probably ever heard of. I know you had a science quiz this afternoon, and one question I would like to hear them ask is, who discovered the Hubble law? Expansion of the universe. It's a trick question. I think it's Edwin Hubble. Actually, it isn't. This guy, Father Lemaitre, discovered it 2 years before Edwin Hubble. Unfortunately, he published it in French in a Belgian journal, so no one read it. But he discovered the expansion of the universe. So he actually then, 3 years later, invented the Big Bang Theory, but he didn't call it the Big Bang Theory. He called it the primeval atom, or the day with no yesterday, which is really what the evolution or the evolution of the universe is. Now, I'm going to give you some details about the universe as we know it. And a friend of mine once said that the definition of science is taking something that is really beautiful in nature and making it into a graph. So I'm going to give you the graph version of this, but I want you to keep in the back of your minds how weird it is that we live in a universe that has a finite size, has a finite age. How did it come into existence? It's a question we don't have an answer to. We now know what happened before the Big Bang. With a very good theory, we actually have evidence in the sky of what happened before the Big Bang. Now, what happened before the Big Bang, we have no idea at this point. So we're pushing back farther and farther into the formation and evolution of the universe. But keep in the back of your mind, it's really strange, it's really wonderful, it's almost kind of scary that we understand something about our universe, that it is finite, something that is achievable using human intelligence to say something about basic properties of the universe. In a couple days, there's going to be a major event in astronomy. On the 12th of July, the James Webb Space Telescope is going to release its first images. Now, the James Webb Space Telescope is the successor to the Hubble Space Telescope, and it's going to give the first images. This is not its real first image. This is from a fine guidance sensor, which orients the telescope to the sky. But most of us in observational astronomy have time on the James Webb Space Telescope. I do. We're going to observe distant supernovae to improve our estimates of the expansion of the universe. But this is the fine guidance sensor image. I think one of the most exciting things that the Hubble Space Telescope is going to do is it's actually going to be able to see the first galaxies forming in our universe. Now, in cosmology, because there's a finite speed to the speed of light, as we look to things farther and farther into the universe, we're seeing things backwards in time because it took time for that light to go from, say, a distant galaxy to us today. So just like the people in the back of the room who are probably about 40 feet away from you, in 1 second, light travels about this distance, 1 billionth of a second, light travels about 1 foot. So the people in the back of the room, I don't see them as they are right now. I see them a couple of nanoseconds in the past. Well, as you go farther and farther out in the universe, we see galaxies farther and farther in the past, billions of years in the past. But we don't have telescopes that are big enough to be able to see the first galaxies in the universe. When the universe was very small, much hotter than it is right now, there had to be first galaxies and first stars formed. We can't do that because the light from those galaxies is shifted from optical, which we can see with our eyes, into the infrared, which we can't see through the normal atmosphere. The James Webb Space Telescope is going to be able to do that. So one of the major first projects of the James Webb Space Telescope is going to be finding the first galaxies, perhaps the first stars in these galaxies exploding. So this is a project that one of my faculty members at Texas A&M is the lead on the project, just to search for the first galaxies. They'll also get spectra of nearby exoplanets and be able to study in detail the atmospheres of the planets, particularly to see if there are biomarkers in the atmosphere. After all, in our atmosphere, we have oxygen. That comes from plants. If the plants suddenly disappeared, all the oxygen would go into the soil and would the oxygen in the atmosphere, oxygen erosion. So one of the other things it's going to do initially is to isolate the light from exoplanets, nearby planets around stars, to see if there are biomarkers in those planets. And if there are, that is oxygen, ozone, methane, and other molecules, that's good evidence there probably is life on those planets. So this is all going to happen in the next 10 years. So the next 10 years of observation astronomy will be associated with this telescope, the James Webb Space Telescope. So on the 12th of July, next week at 10:30 Eastern Daylight Time, they're going to release the first images from this telescope. And it's going to be very exciting. Within a year or so, we probably will have imaged the first galaxies forming in our universe. So one of the really weird things about the universe is that most of it that's out there we can't see. 99.5% of the universe we can't see with our telescopes. It's missing. Now, some of that's missing, we've been able to locate. It's in a thin gas in between the galaxies. But if we add up all the gas, the thin gas between the galaxies and the mass in the galaxies, we only end up with a little less than 5% of the universe. The other part of the universe, 96% of 96% of the universe is dark. And it's made up of two things, which we call dark matter and dark energy. And these, we don't know what they are at this point. So it's weird as an astronomer who uses telescopes, but when I look at a telescope, what I'm seeing out there is really not what the universe is. The universe is made up of this dark sector. Now, the obvious thing is, well, how the heck do you know that it's out there if it's dark? With the telescopes. Well, you can't see it with the telescopes, but we can see what it does to things in the universe. After all, my wife is Croatian, so the Croatian flag there. You see a flag waving off in the distance, you know it's windy. Now you don't see the wind. What you see is the effect of the wind on the flag. It pushes the flag in a particular pattern, which is an interesting and stable equilibrium. But you know it's windy because you see the flag flapping in the wind. The same thing is in the universe. When we look at galaxies, we can see them falling into each other, or we can see them moving away from each other. So we see things pushing and pulling in the universe, just like the wind pushes on the flag. And we can measure that pushing and pulling. And when we do that, it requires that there be two invisible things, dark matter and dark energy. So it's a very easy observation, actually, which you can do with 4-meter class telescopes, the James Webb Space Telescope, and show easily that there are these two components to the universe, dark matter and dark energy. We don't know what they are. Dark matter is like normal matter, but we don't see it. Dark energy is actually anti-gravity. The universe now is dominated by this dark energy, which was discovered in 1998. And towards the end of this talk, I'll tell you about the weird things it's going to do to our future of the universe, because it really is going to do very, very strange things towards the end of the universe. So this is meant to be us, and the rest of it is stuff that we don't see. We know it's there because we see it like a flag waving in the wind. So if you map out all the galaxies in the nearby universe out to, in this case, 1.3 billion light years of travel time to galaxies, this is what you get. This is our galaxy that's put there, so you can't see through our galaxy as well as it does. So that part of the sky is the orbits. But then the rest of it are all galaxies. Each point of this is a piece of galaxy. And what you can see is that it's not just like a shotgun pattern where the galaxies are randomly scattered across the sky. You actually see a rather flocculent or filamentary structure to all the nearby galaxies. You can sort of see circles in this diagram. And inside the circles, there's a lower density of galaxies, and on the edge of the circles, there's a higher density of galaxies. It's a circle here, it's a circle here, clearly a circle here. So why does the universe look like this and not just everything kind of randomly scattered around the sky? So that was a big mystery back in the 1990s, which now with our discoveries in cosmology can explain this. But the most amazing picture of the universe is this. This is called the cosmic microwave background. So this was discovered back in the 1960s by Penzias and Wilson using a discarded telescope, a microwave telescope at Bell Labs in New Jersey, where they found that there was a hiss in the sky, and that hiss corresponded to an early epoch of the universe. We now know this epoch of the universe, they're looking back almost 13.8 billion years to when the universe was about 400,000 years old. And there's, at that time, the universe was very small, because the universe was only that age at that time. The universe was smaller and it's much hotter. And it was so hot at that point, 3,000 degrees, that just like these lights here are, well, these are LEDs, but in fluorescent lights, when the electrons get ripped off of the atoms that produce light, at that point in the universe, early back in the universe has got so hot, the electrons are stripped off the protons. This hydrogen, and you have ionized hydrogen everywhere. A free electron can't get through a photon can't get through free electrons. And so we can't see beyond as farther back in the universe because the electrons block the light. But we can see back to 400,000 years after the Big Bang. And this is what we see. This is a map of temperature fluctuations in the early universe. Blue here is kind of confusing. It's actually hot. And the red here is cold. That's, we got it backwards, but that's the historical artifact. And so they measured, with this telescope, they measured the temperature of the universe in different parts of the sky. And the temperature of the universe in the sky is very uniform at this point. It's about 3,000 degrees. But there are tiny little fluctuations at about 1/10,000th of a degree. Some places that are slightly hotter, and some places that are slightly colder. And this is the map that they made. This won the Nobel Prize a few years ago to John Mather and George Smoot, and later on another team. So this is what the universe looked like 400,000 years after the Big Bang. I just showed you previously what the universe looks like today. Here you can also see kind of a flocculent structure. You can kind of see that there are circles in the sky. So there's something going on. What's causing the universe to have a structure that looks like this? What I want to do now is I kind of want to give you a dog's breakfast view of what we know about the universe. There are many things that are weird about the universe, some of which we understand why, but most of them we don't. So the fun thing about science is not, to me, learning what we already know, but it's working on stuff that we don't understand and we don't know the answer to yet. So I'm going to give you a large list of things that we haven't figured out in cosmology. And a number of these things, if people are going to astrophysics, you guys are going to figure this out. We haven't figured out these things at this point. But this gives you an idea of some of the strange things that are going on in the universe as we see them today. This is a picture of the Hubble Deep Field. The Hubble Space Telescope, a 2.5 meter class telescope, was launched back in 1990 or so. And one of the things that it did, which was an idea of the director at the time, Bob Williams, was to point the Hubble Space Telescope and take an image over and over and over and over again for basically 3 weeks, and then add all the images together to get the deepest view of the universe. And you can't appreciate this picture because these lights are very bright, but this is the deepest picture into the universe that we have. There are 4 different Hubble deep fields. This is the first one that came out. Everything that you see in this image is a galaxy. There are absolutely no stars in our galaxy that appear in this image. So we picked a particular part of looking out into the universe that avoided all stars. So the amazing thing in this picture is that it's still black in between the galaxies. Galaxies are cool. Actually, this is a very simple thing. You can go to this image and count up the number of galaxies, and then multiply by a ratio of the size of this image to the whole sky, and you yourself in about 5 minutes can calculate how many galaxies there are in the universe, just based on the number of galaxies in a particular image. Most of you probably know who this is. This is Edgar Allan Poe. So why is he in cosmology? Well, Edgar Allan Poe was a very brilliant man. He was kicked out of 3 different universities for strange behavior, but he was a brilliant mathematician. It was actually Edgar Allan Poe who first showed why the sky is dark. Now you think the sky is dark when the sun goes down, right? That's not the reason why the sky is dark. The reason why the sky is dark is that it's dark in between the stars and the galaxies. Now that may not seem very surprising to you, but it is, because if the universe was infinite, or infinite in some ways, That shouldn't happen. So I want you to imagine in your mind's eye, say you're going down a country road, and next to the country road, a farmer has planted a row of trees. And as you look through the trees, you can see the fields in the background. Now, if this farmer had planted 2 rows of trees, we now have 2 rows, and now you can see only a little bit of the fields in the background. If you planted 3 or 4 or 5, you see less and less. As a matter of fact, if you planted a large enough number of rows of trees, sooner or later you could not see the trees, the field through the trees. You can't see the forest through the trees. So that's exactly what's happening here in the universe. If the universe was infinite, every direction that which I look at, I should be able to see a galaxy or a star. And since our sun is 6,000 degrees, even though that star is very distant, the little disk is still representative of 6,000 degrees. The universe is infinite. Every direction I look in the sky, I should see a star. And therefore, every direction in the sky should be 6,000 degrees, which means when the sun goes down, the whole sky should still be 6,000 degrees, the same as the surface temperature of the sun. That's called Olber's paradox. And Edgar Allan Poe, in his crazy book called Eureka, which is a very strange book to read, which has parts of it which are totally incomprehensible. It's kind of like a fever dream. He has some really good mathematics. He first showed that the fact that the sky is black is direct proof that the universe is finite in some way. So all the big telescopes that we have, the most profound observation in cosmology is that when the sun goes down, it gets dark, because that shows you the universe is finite. I'm not saying it's finite in age or size. It's complicated because there's expansion of the universe and redshift and all sorts of other things. But it still is prime evidence that the universe is finite. So when you go out and observe tonight, it's dark. Appreciate the fact that you're able to do astronomy because the universe is finite. So now I'm going to go through the stock breakfast of weird things about the universe. So the first thing I want you to come away with is that we now know the universe didn't start with the Big Bang. We now can see things that happened before the Big Bang. Another weird thing about the universe, again, the random things I'm telling you that we haven't completely understood, is there are no magnetic monopoles. That is, we have an electron and we have protons. These are positive electron charges and negative charges. And that's another good science quiz question. Why are electrons negative? It was Benjamin Franklin who decided that electrons are negative. He didn't know they were electrons, but he studied current. It was Benjamin Franklin that has caused us to this day to say that electrons have negative charge. But if you take a magnet, you break it in half, you don't have just a north pole or south pole, you know about 2 magnets because another 2 poles appear magically. So a magnet always has a north pole and a south pole. But why is that? Why isn't there just a charge which is a north charge and a south charge? Why do we always come in pairs? We don't know. Good question. Another weird thing is that we know the universe is made up of matter. Now there's matter and there's antimatter. So there's an electron and there's anti-electron. It's a proton and anti-proton, neutron, anti-neutron, etc. Why is it that all of the stuff we see around us is matter? Well, an obvious answer is that there were equal amounts of matter and antimatter, they would annihilate, and there would be nothing left over except high energy photons. So there has to be an imbalance in the universe as to there being a little bit more matter than antimatter. And balance is incredibly constant, but it's very small. For about every 1 billion plus 1 matter particles in the universe, early in the universe, we had to have had 1 billion antimatter particles. And all of those annihilated to produce photons that we see in the universe, except the 1 matter particle that was left over. When we look at a distant galaxy, when we look at a nearby galaxy, do we know it's made of matter or antimatter? We actually know that the nearby galaxies are made up of matter because those galaxies, when stars explode, expel material. That material can arrive here at high energies called cosmic rays. And we know that those cosmic rays are mostly made up of matter. So we know the nearby universe is mostly made up of matter. The distant galaxy, I don't know if it's matter or antimatter. But since the nearby universe is mostly matter, it seems to be pretty safe that the rest of the universe is made up of matter. So why is the universe so carefully balanced that for every billion antimatter particles in the early universe, there were 1 billion plus 1 matter particles? We don't know. 94% of the galaxies that we see today, we will never see when they're 14 billion years old. So let's say the universe is roughly 14 billion years old. We argue about whether the universe is 13.2 or 13.8 billion years, depending on the expansion of the universe. But let's just call it 14 billion years. So imagine our universe. The universe is expanding. Imagine that we could freeze the universe right now, and everywhere in the universe is the same age. And I could jump to any galaxy instantaneously and appear there. And so today, those galaxies everywhere in the universe are the age of the universe, roughly 14 billion years old. Presently, there is light leaving those galaxies. As the universe expands, that light goes along the universe. The light that's leaving that universe, those galaxies today, almost all of the galaxies, that light will never reach us. Not only about 6% of the galaxies in the universe will we see the light that is leaving those galaxies today. Now, why is that? It's actually not a very complicated explanation, except for one thing that I have to dissuade you of. We all learn that the speed of light is constant. You can't go faster than the speed of light. That's true in the kinetic sense. I can't push things faster than the speed of light. But there's nothing in the theory of gravity that says the universe can't expand faster than the speed of light. So as the universe expands and the light is propagating away from those galaxies, that light is propagating against the expansion of the universe. So imagine a salmon swimming upstream. If the salmon can swim faster than the stream, the salmon can swim up the stream. But if the stream starts going faster than the salmon can swim, the salmon is carried down with the stream. That's what's happening in our universe today. That light from all the galaxies today, 14 billion years old is the universe, is leaving, some of it is in our direction. But over the time that light is propagated towards us, the universe is going to expand faster and faster and faster. It's actually going to expand faster than the speed of light. So these photons, which are swimming upstream against the expansion of the universe, are going to get carried away by the expansion of the universe and never get to us. So when I look at this deep image, like the first image I showed you from JWST, all of those galaxies today are 13.8 or 13.2 billion years old. That light is leaving them today. We will never see those galaxies when they are 13.8 billion years old, because that light's never going to get to us because the universe is going to be expanding too fast. So it's kind of weird that most of the universe that we see today, we will never see when that light is actually 14 billion years old. Another weird thing is that space is flat to 1%. Now, what do I mean by flat? I don't know if they teach you this in high school, but there's a formula for some of the angles in non-Euclidean geometry where you sum the three angles in a triangle, it's equal to pi, plus or minus depending on whether it's positive or negative curvature. This particular factor, the area divided by the radius of curvature squared. So in a flat universe, you have angles, you have 180 degrees. In a positively curved universe, you add up the angles, and they're greater than 180 degrees. So imagine a sphere like the Earth, and let's take a big triangle on the Earth. Let's start out at the North Pole. We draw two lines of longitude that come down, hit the equator. And let's start those two lines at a 90-degree angle. So they come down to 90 degrees and hit the equator. And hit the equator, that part of the equator becomes the third part of the equilateral triangle. When they hit the equator, it hits perpendicular. So you now have three angles, 90 degrees, 90 degrees, 90 degrees. So when you add up those angles, you end up with 207, don't add up to 180. So if we can measure gigantic triangles in the sky, which we do, and add up the angles, I can tell how flat the universe is. Does it add up to 180 degrees? Or is it like this, less than 180 degrees? Or like that, which is in the closed universe? Turns out it's basically 180 degrees. The universe is flat to about 2%. That's a weird fact. Why is the universe geometrically flat. It doesn't have to be. It can be any one of these shapes. So there must be a fundamental physical law that says the universe must be flat. We don't know what that law is. Some of you are going to have to figure it out. We haven't been able to do it. It's even weirder than that in cosmology. So what is pi? Pi is equal to the circumference of the circle divided by its diameter. You'll notice that. But in non-Euclidean geometry, pi is not a constant, it's a variable. So again, let's think of this gigantic triangle that's the Earth. So if we draw a tiny little circle at the North Pole and measure the circumference of the diameter, we'll end up with pi. But if we take that circle, lines of latitude, and bring it down to the equator, now let's do the calculation again. Let's assume the radius is 1. So the equator is 2 pi. The diameter, you've got to go over the pole and come down on the other side. So that's half the circle. So that's equal to pi. So the circumference, 2 pi, divided by the diameter, pi, is equal to 2. And so on a sphere, the value of pi is actually a variable. It's not constant. And even if you think about it, and I'll leave this to you as a challenge, actually pi doesn't even have a single value. On a sphere, pi has 2 values. Think about it. If anyone can get the answer before the end of the talk, I'm interested in hearing your answer. But it is true, there are 2 values for pi on a sphere. But we don't have to worry about this because we now know the universe is geometrically flat. So I said we have clear evidence for the universe prior to the Big Bang. The other thing is that in an expanding universe, actually nothing is moving. That's a strange concept to wrap your head around. But when I look at a galaxy and it appears to be moving away from us in this expanding universe, actually things aren't moving. What's happening is the space is stretching in between those 2 points. And that's why you can go faster than the speed of light. There's no kinetic energy involved. The universe is stretching gravitationally, but nothing is pulling the universe in that stretching process. So it looks like galaxies are moving away from us, but actually what's happening is the universe is stretching between different points of the universe. Another thing which I seem to be the only one that ever points this out. People who work in this field know this, but they never say it this way. We can actually observe independent universes, and we actually have a picture of those independent universes. And I'll talk about that towards the end of this talk. So we actually see independent universes in the early universe, not just one universe, but thousands of universes. Another strange fact in the universe is that when stuff is far away, it doesn't get smaller. Now, if you see a tree that's nearby, it has a large angle relative to you. If you move it far away, it gets smaller. So for us, our eyes and our brain adjust to figuring out how far away something is by what the angular size is. I know that that tree or that car is far away because it has a small angular size. In cosmology, the farther something away is, it still has the same angular size in the sky. So when you see a deep picture that's going to come out from the James Webb Space Telescope in a couple of days, you'll see small galaxies and you'll see big galaxies. We don't know what the distances to those galaxies are, but because the angular size of those galaxies doesn't depend on the distance, you can immediately say the galaxy that looks bigger is bigger, because things don't get smaller in a universe that's expanding due to general relativity. It's a weird optical illusion. Things that are farther away will get smaller. They have to be very far away for this to happen. We're talking about this universe. The number of galaxies in the universe we can count up, or we can estimate it's about 2 trillion. The number of galaxies in our universe is increasing. So our universe, as it's getting older, our universe is expanding and getting bigger and bigger. And as the universe expands, theoretically, we can't observe this because it's very slow, but theoretically, new galaxies will appear at the edge of the universe. And so the number of galaxies in the universe is increasing over time. But that's not going to happen forever. In about 15 billion years, the process is going to start to go backwards. Because as the universe is expanding, it's expanding faster and faster. That's what we discovered in 1998, the accelerated expansion of the universe, which won the Nobel Prize in 2011. So as the universe expands faster and faster, the distant galaxies appear to be stretched away from us faster than the speed of light. Now, those galaxies are emitting light. If they're moving away faster than the speed of light, we're never going to see them. So as the universe expands faster and faster, those distant galaxies are actually going to disappear from our sky. So in about 15 billion years, our universe will have new galaxies appear at the edge. But by that time, the edge is going to start moving faster than the speed of light is, and we're not going to be able to see the new galaxies. And as the universe expands faster and faster, distant galaxies begin to disappear, and the whole sky begins to turn black. Only the few galaxies that are nearby, a couple hundred million light years of our own galaxy, will remain within our universe over the next 100 billion years. After that, most of the galaxies will appear in the sky. So we're living at a special time when we can see most of the galaxies in the universe. There are only some few percent more that we'll see in the future that are going to come into our universe. It's kind of a weird fact. Another weird thing, and this one really bothers us, is the Higgs boson. Some of you probably know what the Higgs boson is. It's a particle that's discovered at the CERN accelerator in France and Switzerland. It's a particle which imparts mass to some particles. Without the Higgs boson, an electron, for instance, would have no mass. So they predicted what the mass of the Higgs boson is about 100 times that of the mass of a proton. Then they found it was about 126 when they actually did the measurement. But that particular mass is a strange number because if it's slightly smaller, that particle becomes unstable, and therefore the concept of mass becomes unstable. So the Higgs boson is at a mass that is close to causing the universe to be totally unstable. Now, people have tried to calculate how unstable is the universe. That is there a point in the future of our universe, or even the universe today, where one of these Higgs particles actually goes unstable and turns into energy, therefore everything around it loses its mass? Well, we think that may not be the case, but the Higgs boson mass is right at that point. There's no reason why it has to be there as far as we know. But the Higgs boson being at the point which makes the universe almost unstable makes you think that has some sort of profound effect on cosmology. Maybe somehow this in the fact that the Higgs boson, which gives mass to particles, but it can actually decay. When it does decay and takes the mass away from the particles, maybe that ends up being a seed, which then propagates out into the universe and destroys our universe. That's what we thought. But this is a coincidence that we can't explain away. So I hope one of you can figure this out. Why do we live in a universe where a fundamental force, a fundamental particle, which gives mass to everything that we have here, why is that an unstable particle? There's no reason. Well, I'm not going to go through all of these because I have a whole list of them, but let me just pick out a few of them. The universe is 13.8 billion years, but the most distant galaxies are farther away than that. Well, that's because the universe has been expanding. So when someone says the universe is 13.8 billion years, that doesn't mean the most distant object is 13.8 billion light years away from us, because that galaxy over this period of time too far away from us. So if I froze the universe today and jumped to the most distant galaxy, the ones that the James Webb Space Telescope will discover, it would be about 46 billion light years that I'd have to travel. So the present size of the observable universe is about 46 billion light years. The light from those galaxies has been traveling 13.8 billion years to get to us, but since then the universe is expanding. This third one I already talked about. The galaxies at the edge of the universe in about 15 billion years are going to begin to disappear from the sky. Any galaxy that is presently farther away than 66 billion light years, we will never see. So again, if I took the universe and froze it, stopped all the expansion, was able to jump to any galaxy anywhere in the universe, the galaxy right now is more than 66 billion light years away from us. That light is never going to reach us. And we presently can't even see that galaxy. So that's the edge of the universe that we will ever see, at 66 billion light years. So the combination of the finite age of the universe and its expansion means that even if we're in a universe which is infinitely large, we're only going to see a small part of that universe. And why is that? It's a very, very strange concept, but with the laws of cosmology as we know today, it's another thing that's really annoying for us right now in astronomy, and I'll talk about that at the very end, is that we can't even measure the expansion of the universe. We got two different numbers. I can measure the expansion of the universe by how fast galaxies appear to be moving away from us. That gives me one number. But if I take that image from 400,000 years after the Big Bang and extrapolate what we know in that image till today, I get a different rate for the expansion of the universe. And these two numbers are very close, and it was thought that there was just some sort of error in the way that one of us was doing this particular calculation, me being one of the people doing the calculation. But we now have measured precisely the expansion of the universe in these both methods. Both of these methods give different numbers. So there's missing physics. There's something that is causing our calculations from the expansion of the universe early in the universe, and expansion to today, only for two different numbers. We don't know the answer to that. I've said something about dark energy, which is 70% of the universe. It acts like a antigravity. You learn calculus, you now know when you integrate something, you end up with a constant integration. Well, dark energy is the constant integration of general relativity theory that Einstein came up with. And Einstein set it equal to zero, as almost everyone else has done, until 1998, when we discovered it actually wasn't equal to zero. It was an incredibly small number. But the basic calculation, if you try to predict how big the cosmological constant is, you end up with a number that is off by about 10 to the 121 power. That is, the elementary calculation for what the cosmological constant is, what dark energy is, what is driving the expansion of the universe, is off by that factor. That must be the worst prediction ever done in science. Off by 10 to the 121 zeros. We don't know the answer to that. So the cosmological constant, which is driving the expansion, the anti-gravity expansion of the universe, is completely not understood. And it's off by that factor. No idea why. One of you will solve it. I'll give you that. So he said these things. So the total number of galaxies we'll see before the end of the universe within our observable universe is about all of the galaxies. So for an observational astronomer like me, this is the census of what we see in the universe. 96% of the universe is dark. It's made up of 70% dark energy, anti-gravity, which is pushing the galaxies apart, dark matter, which is matter, normal matter plus a type of matter that seems to add on to normal matter, and that's about 26%, about 30%, only about 4.5% of the universe is normal matter, that is you and me. And we can only see half a percent of that in stars, and about 0.12 is in neutrinos, and the rest is in other stuff. So this is the sense of the universe. When I go out with a telescope and I look at the universe, this is what I see, that 0.5% in stars. The rest of it, at least we know where the 4.5 normal matter is. Again, it's in the thin gas in between galaxies. But the dark matter and the dark energy, you can't see it. You can see it like it will fly away from the moon. We know it's there, but we have no explanation. Even stranger things. Why does mathematics work? Is mathematics a universal law? And yet there was an intelligent civilization somewhere else. Will they invent the same mathematics as we would? I would think so, but I don't know. And again, the question I have asked first is, why can we understand the universe? Why is it understandable? The thing that no one ever thinks about is this third one, this space. So I've all heard of Star Wars, travel in space and time. But space and time are not the same. The basic universe is four-dimensional, but it's not four-dimensional in the standard Cartesian sense. So we describe the universe, distances in the universe using x, y, z, and time. So the distance from here to another point in the back of the room, I know the x distance, the y distance, and the z distance, and I square those and add them up and take the square root, I can calculate the metric distance to that point. So I have three coordinates like this, X, Y, and Z. As a human being, I have freedom of will to move in any of these three directions. I can move with X like this, move with Y like this, and even jump up and down if I want to. So I have free will in three directions, provided I go faster than the speed of light, because kinematically you can't do something faster than the speed of light. But the fourth coordinate, time, is completely different. Time is always stuck at one point. And that one point we call the present. I don't have free will to go back and forth in time as I do in these three coordinates. We're stuck at one point in time always, which is the present. So why is that? Why is it there's not freedom of will in time? So how many of you saw the movie Interstellar? Well, a lot of you did. When I first saw the movie, I came away at the very end. Matthew McConaughey follows it as the hero into the black hole, etc. I thought, like, this is the stupidest movie I've ever seen. How can Hollywood invent this sort of stuff? Well, it turns out that stuff that was invented was actually invented by Kip Thorne, professor of theoretical physics at Caltech, won the Nobel Prize. So I was clearly wrong. It does make sense. So there is something in that movie which Kip Thorne predicted, which I didn't know about. Well, I knew about, but I never visualized it. And actually, Kip Thorne never visualized it too. Is that you can actually travel backwards and forwards in time in a very special circumstance. And that circumstance is falling into a black hole, something I would recommend. You're falling into a black hole, and the black hole is spinning. And in that case, these three coordinates, X, Y, and Z, rotate a little bit in 4 dimensions. And the time coordinate where you're stuck at one point actually also rotates so that X, Y, and Z gets a little piece of time, and time gets a little piece of X, Y, and Z. So inside a rotating black hole, which is how Matthew McConaughey was able to push books to the top of his dollar or whatever, that actually is a prediction of general relativity, something we can never prove because falling in a black hole, well, we figure it out when we fall in a black hole, which can never tell anything about it. So that actually is possible. We do have free will in the 4th dimension of a spinning black hole. Not that it really helps us, mathematically it's the case. But the point I want to make is that when we talk about 4 coordinates, X, Y, Z, and time, those 4 coordinates are not all equal. One of them we have no free will in. Why is that? Say one thing about a black hole. This is a lake in California. You're familiar where I grew up. It's called Lake Berryessa. This is a spillway at Lake Berryessa. When the lake gets high enough, it is this incredible round spillway where the water flows into it and then down into a tunnel which comes out at the bottom of the dam. This is a perfect analogy for a black hole. A black hole, among many things, light can't escape from a black hole. But inside of, near the surface of the black hole, what's happening is that space and time is falling into the black hole constantly. So that just like water goes over the edge in the spillway, the volume of water over time increases. The size of the hole here doesn't increase, it's the same size, all spillway, but the amount of water going into the black hole, into the spillway increases. The same thing happens with the black hole. The black hole is roughly the same size, unless it creates a little bit of mass. But the volume of the black hole increases over time. It's a weird concept. The black hole surface doesn't change its size, but as space and time falls into a black hole, the volume inside the black hole actually increases. Just like water flowing over the spillway. The size of the spillway, the circle doesn't change, but the volume of water increases over time. And the strangest of all, which is what I want to end this lecture on, are why are there 3 universes? I already talked about what the contents of the universe was. We already talked about the future of the universe, but let me just say it again. We're basically all dead. Stars, most of the gas in the galaxies have been used up. So our galaxies, although are still forming stars, they're forming stars at a rate that's about 1/100th of what they used to. So for all intents and purposes, galaxies are not forming stars and they're dead. All the gas has been used up. We're going to collide with the Andromeda galaxy in 4 billion years. In 70 billion years, 100 billion years. The number is very flexible, but it's about 100 billion years. Most of the galaxies in the sky will disappear because the universe is expanding so quickly that the light will never get to us. And then we don't even know what's going to happen after that. So two things can happen. The universe, as it expands faster and faster and faster, all those galaxies disappear. But one of the things that can happen is the galaxies that are close enough to each other, they will remain bound and they will just slowly die as all the stars die. But if this dark energy is a slightly different value, dark energy actually will go into the galaxies and pull the stars apart. So over time, all the stars will disappear from the universe. Then it'll go into the solar systems and pull all the planets away from the stars. And then it'll go into all of the atoms and pull all the electrons away from the nuclei. It'll go into the nuclei and pull all the quarks apart from each other. Everything gets ripped apart. And that's called the Big Rip. And the fact that our universe is flat, just like the Higgs boson, is the tipping point between whether the universe rips itself apart in the future or whether we have a slightly less glorious death. That is, the galaxies, the nearby galaxies, will always remain gravitationally bound, and but all the stars and the stuff will stay gravitationally bound. Right now, that's one of the most important things to measure. How flat is the universe? Because if we know how flat the universe is, I can predict whether the universe in the future is going to rip itself apart. It's nothing to do with Higgs boson. This is another way of us dying. It'll rip us apart, or whether the universe will die more gracefully. And so we don't know the answer to that. But the more we measure how flat the universe is, the more it appears geometrically flat. But if it's slightly away from that, one direction or the other, will cause the universe to either gracefully die or die a horrible rip death, which is called the Great Rip. So that's one of the most interesting things to measure. Theoretically, right now we think the universe is flat, but it doesn't have to be geometrically flat. Remember, all the angles add up to be. So let me, at the very end here, give you three universes. So there's the observable universe. The observable universe is obviously anything we can observe. That doesn't mean there are not other things out there. It's just our universe has a finite age. Anything that's farther away is 13.8 billion light travel time. That light hasn't gotten to us yet. So it could exist, but we just don't know at this point. So the observable universe is always the age of the universe. So if I look backwards in time, say a billion years after the Big Bang, that universe is much smaller and there's fewer galaxies in it because the universe, the age is only a billion years. As the universe gets older, more galaxies appear at the edge until dark energy takes over and moves the galaxies faster than the speed of light. We're not at that point yet. So the observable universe is the universe of the astronomers. That's the one that I claim. It's 13.8 billion years old with one value of the expansion of the universe. It's 13.2 with the other expansion of the universe. So it's 46 billion light years in radius as the universe is expanding at this stage. So workshop that I used to go to all the time when Stephen Hawking was still alive. He would come to Texas A&M every year because a number of his students working on the university in string theory. See Hawking there. This is Alan Guth, inventor of the inflationary theory, which is the standard theory of cosmology right now. Every time I've given a talk, Alan Guth has fallen asleep. I've discovered, though, it's not me. He falls asleep at every talk. Anyway, that's his natural quantum state. Stephen Hawking is there with his nurse, and I got to chat with him, so to speak. If you walk around to the other side and look at what Stephen Hawking is doing, every time I look on what's going on his computer screen, is he's writing his next book. So Alan Guth is asleep, and Stephen Hawking is writing his next book. It's not the most dynamic writing. So he's Fernando off on the left there is awake. And then there's a guy in the distance drinking 2 bottles of wine. So it's an unusual type of work. And so that's the inventor of the inflation. So going back to this is a picture of the universe when the universe was 380,000 years old. You can't see farther back because the universe is too hot then. and you can't see through free electrons. There are hot spots, there's blue stuff, there are cold spots, which is red stuff. But if you look at this, there's one unusual aspect of that your eye sees, but you don't consciously think of. What your eye sees is there are patches, which are interesting. Patches, where the little sections that are large sections that are slightly warm and large sections that are slightly cold. But what your eye sees, but is not telling your brain, is there's actually the spot size. This whole image is made up of something that's about the same size spot. Now, some of the spots come together, so they look like bigger spots, some of them are partial spots. But on the average, there's one spot size in this image. It's an expanded part of the image, and there's just a standard spot size in this image. And they're bigger spots, but they're fewer. One size spot is always about the same size. If you take this image and center on every spot, and then average all those spots together, this is what you end up with a perfect circle. Kind of weird. Actually, what you're seeing is you're seeing independent universes at this point, because the universe is only 380,000 years old. So that means if you happen to be alive at that age of the universe, when the universe was very young, you could only see out 380,000 light years away from it, because the rest of the universe is farther away, which exists that we know today, that light hasn't gotten to you. So every one of those little spots that you see there is an independent universe at that age of the universe. And since there are a couple thousand spots in that image, we're seeing a couple thousand independent universes. Now, in the meantime, as the universe has gotten older, all those little spots have merged into our present observable universe. But back then, each one of those spots was independent. One spot could not see the other spot because they're separated by more than 380,000 light years. It's actually, there's a square root of 3 in here because the spot size depends on the sound speed, but it's roughly the radius of 120 spots is the age of the universe times the speed of light. So when you look at the CMB, this image which has slight temperature fluctuations, those temperature fluctuations have an average size, and that average size is the age of the universe at that time. Each one of those spots can't see the other spots. So we have direct evidence from independent universes earlier in the universe. A good analogy is taking a bunch of sand and throwing it into a pond. When it hits the water, you have tiny little rings, waves that propagate outward. When the sand initially hits, all of those little rings are independent. But over time, the rings spread out and all overlap with each other, and they all disappear. So over time, each one of those little spots you see in that image has expanded over time to what our universe is today. But because there was one specific spot size in this early universe, if you take that spot size, that CT over square root of 3, and expand it into how big it is in the universe today, that's exactly the size of those bubbles that I showed you in the first image of the galaxies that are within a billion years of our own, billion light years of our own galaxy. So we see the vestiges of those little spots in our present universe. So we can take an image of this early universe and map it into our present universe. Just like all the little rings of the pond that expand over time, you can still see evidence for those initial temperature fluctuations in the nearby universe. And that turns out to be one of the strongest ways to measure the expansion of the universe, comparing the spot early on in the universe with the size of those rings that we see today. To me, this is just a brilliant fact that I can look at an image in astronomy from light that comes from very, very far away in time and actually see universes that are independent of each other. That's the observable universe as it was 380,000 years ago. So the observable universe is the universe that we see today. Now, if I take that universe that we see today and shrink it back in time, now remember that as you shrink back in time, the observable universe at that time is the age of the universe. So I'm not doing that. I'm taking every galaxy that we see today, and we shrink it back to the time of the Big Bang. How big is that? Well, if I take all of the galaxies in the universe, and I move them back to the very beginning of the universe at the big time of the Big Bang, it's about 1 meter across. So the size of the observable universe when our observable universe at the time of the Big Bang is about the size of a beach. Every galaxy we see in the universe today fits into that beach ball. Obviously really hot and really dense, but that is the state of matter at the time of the Big Bang. But this is not the whole universe, because we're just a small part of it. We're the part of the universe that we can see, which is 13.8 billion years old. There's probably a much bigger universe that we're inside of. How big is that second universe? Well, we don't know. It could be infinite. But we do know what its minimum size is based on the measurement of how flat the universe is. So the second universe, which is kind of like an onion, which is larger than the observable universe, is, well, the best estimate we have right now, this was 250 meters, was what it was a couple of years ago. It's now about 600 meters. So the minimum size of the universe into which we're expanding at the time of the Big Bang is a little less than a kilometer across. So we're a tiny little point, our universe, inside this much larger universe. This universe, this one that was expanding into, is huge. I don't recall what the number is, but very, very large. So our observable universe is inside another universe. We're expanding into this other universe, but because of dark energy, we're able to see a small part of this larger universe before it all disappears as the universe expands faster and faster. There's no name for it. I call it the meta universe. So far, this hasn't caught on yet, but that's what I like to call it. In this microwave background radiation, one of the things we always search for are circles. If you take two soap bubbles and they happen to merge with double soap bubble, the place that they intersect is a perfect circle. So our universe is somehow made at the same time as another universe, or attached to another universe. We should see a circle in the sky peering into another universe. So anytime we have make a map of the universe like the CMB, what we search for are large circles in the sky, because that would be something that is evidence for another universe that's touching us. And Roger Penrose, who won the Nobel Prize in Physics a few years ago, a friend of mine, this is his theory. Only Roger sees circles in the sky. He takes that map of the CMB that you can find circles. It looks something like this. There. But none of us statistically can find a circle, so we don't know Roger is smoking. But Roger is this is his thing called cosmology. It may be true. It's a very interesting time to talk about it. It's a very interesting theory. So we search for circles in the sky. We haven't seen them yet. We've seen small circles, but we know those are the spots that we see early on in the universe. That would be evidence of the previous universe. So this is the size, roughly the size of the universe we're expanding into liquid nitrogen, liquid tanks. So that's the meta universe. And finally, is that all of this had to form in something else, because the Big Bang had to come from somewhere. And so Alan Guth, the guy that was asleep, came up with the theory of inflation, which postulates that there's another universe that's much, much bigger. And in this universe, there is an energy field, which we don't know what it is, but we can mathematically create a model. And in this energy field, due to basic laws of physics or quantum mechanics, there should be little energy fluctuations that appear and disappear. And one of these energy fluctuations happens to expand into our universe as a Big Bang. But this Big Bang, our universe, is just one energy fluctuation in a much, much larger universe. And how big this universe is, we don't know. But this is one estimate, kind of a wild estimate, the best estimate we have, is that the universe out of which our Big Bang has come from is at least 10 to the 10 to the 30 power larger than our observable universe. I don't know what to do with this. Personally, I didn't know which way do you read it. Do you read it like this, or do you read it like this? Turns out to read it this direction, so I'll read it. And for another mathematical challenge, Since this is kind of a total number, what is pi to the pi of pi? Is pi to the pi to the pi a integer, a rational number, or an irrational number, or a transcendental number? You would think that this would be a transcendental number, but I can show you a number to an irrational number to the same irrational number to the same irrational number that turns out to be an integer. And it's really easy to figure out. Square root of 2, yeah. So this is square root of 2. Square root of 2 in there, you get 2. So you can take irrational numbers to irrational numbers and make them an integer. So this has nothing to do with cosmology. This is an interesting mathematical question that hasn't been solved. Is this number an integer? Probably not. Okay. So finally, I want to get back to this image. That's my final slide. Oh, actually, so again, this is the universe. The temperature fluctuations early on in the universe, 380,000 years after the universe formed. So what you're seeing here, in 1/10,000th of a degree, 3 degrees of fluctuations, a little bit hotter, a little bit colder. All of these fluctuations came out of the inflationary universe. This phase earlier than our Big Bang. And what you're seeing here is all the way back out of this original idea of inflation. Each one of these little spots is just a small energy fluctuation of a subatomic particle. So when we look out at the sky, according to these theories of cosmology, which have 3 different universes, one inside the other, we go all the way back to the inflationary universe and look at the little energy fluctuation out of which our universe grew. Inside that energy fluctuations are other energy fluctuations. That's what you're seeing. So when you look out at the sky and you see those big rings of galaxies that are 500 million light years size, one of the first images I showed in this image, what you're really looking at is the inside of what is essentially a subatomic particle. So even though I've given you 3 different universes inside each other, the ultimate universe that we know about, the inflationary universe, of which we actually have some pretty good data that shows that it exists. The structure that you see is actually the structure inside a subatomic particle. So that maps the largest scale in the universe, or universe, down to what's inside the subatomic particle. So the galaxies that are scattered across the sky, their origin and their distribution is the same as what happens inside a subatomic particle. But that subatomic particle appeared in an early form of the universe first. So I need 3 universes. The observable universe, the thing we're expanding into, the meta universe, which is also called the Big Bang universe, the thing out of which the Big Bang universe came, which I call the Ur universe, Ur being the ancient city in Babylon, which is a prefix in English, which means primitive. So these are the 3 universes that we have. And this is our present cosmology. We use these 3 ideas to describe everything we see in cosmology. So talk about that. Here's an artist's rendition of a chaotic universe. So if our universe, our Big Bang universe, came out of an energy fluctuation in this early universe, there must be other energy fluctuations happening in this gigantic early universe. And so each one of these, is an artist's conception of it. There are many, many different Big Bangs. Those Big Bangs could have happened at different times. They could be happening now, they could be happening way in the past. But if you postulate that our universe came out of an energy fluctuation, like Alan said, because of quantum mechanics, there must be an infinite number of other universes that are constantly forming. So this is called the chaotic universe. So a prediction, which we can never verify, but a prediction of inflationary universe is that we live in this gigantic Ur universe where the other universes are infinite at one time. Artist perception. It's a theory of Andrew Linda's Stanford. Just to end up on something more realistic, since most of you are going on to college, obviously, and many of you are interested in research, I just thought I'd show you what kind of research looks like in terms of astrophysics. So this is a paper my postdoc is publishing next week. It's called the Carnegie Supernova Project Measurement of the Hubble Constant using Cepheid, the Giant Branch, Surface Budget, Fluctuation, Calibration, and Type 1 supernova. And this is a list of authors, a list of everywhere, all where these authors are. Astronomy is now a science where we work in large groups. In this case, we have roughly 40 or 50 people in this. They're from all over the world. They're from Chile, Argentina, Australia, Denmark, United States, Canada. We never meet as a group together. We all do our science over Zoom. Two of the people here are Nobel laureates. Brian Schmidt, who is my collaborator in the Z project, and Saul Carter, who is the head of the feeding project, or part of this collaboration. This is just typical thing. This is the data product in the sense that you come out with when you're a practicing scientist. You publish an article like this, it appears in the journal. We hope that some people read it. A lot of people will just look at what the number is. So the reason why I kind of show this and I'm kind of bragging is that we're actually going to go after one of our third collaborators, who is the third person who won the Nobel Prize out in Greece, because we're going to challenge Adam's value for the Hubble constant. So next week we're going to let this thing hit the press, so to speak, called the Astro Archive. And we're going to say that something that their group has been doing is wrong. And so there's going to be fireworks. But what I want to show you, this is what we do for a living. This is present science. Large groups all over the world, traveling all the time to nice conferences and places all over the world, lots of different collaborators. And to me, it's really exciting. This is what I love to do. I love trying to figure out what we do together. Anyway, thank you very much.
Dr. Suntzeff, wanted to give you a small token of our appreciation for coming all this way and giving her.
Thank you.
Yeah.
It's kind of late, but I'd like to take any questions, just a few questions. I'm sure that this is all. It's not obvious to me. Yes.
Sorry, so you said how the universe is flat by having a triangle. How exactly did you get the triangle?
Great question. How do you calculate the triangle in the universe? What we do is, well, there are basically two directions. One is a radial direction, and the other is an angular direction. So you pick two galaxies in the sky, and you can measure the angular separation, say 90 degrees. We can also measure the distance to those galaxies using supernova, this type 1 supernova, which my team invented, which we can measure distances to 6%, which is more accurate than the method. So we now have three sides to the triangle. And so although one side is an angle, that size can be turned into a linear size by the cosmology. And so we can then calculate what that triangle is, and sort of indirectly calculate what the sum of the angles. We don't actually do that in the paper, but that's what we're doing in another type of mathematics. You can describe it in different ways, but ultimately what we're doing is measuring the sum of the angles. So we measure distances in two galaxies and the angular size in the three. Yeah.
So you talked about how Edgar Allan Poe showed that the universe must be finite because the sky isn't just completely bright at night. But why couldn't there be an infinitely sized universe with a finite number of stars?
But then there are parts of the universe which have no density. So that's possible, yeah. But then that's in a sense finite. You're saying that the question is, why can't we have a universe which is infinite in size, but there are finite number of stars? That's really your question. It's maybe possible, but then you're still using something that's finite, which is a finite number of stars. It's a very direct observation. There are various ways of interpreting why the sky is black. That would be one of them, but you're adding an element of finiteness to it.
mentioned like that same kind of like swimming, that's like a green kind of television. I'm just kind of curious. You said that the light's escaping as the universe is expanding, but the galaxy are the galaxies moving with this kind of person, or you said that as the universe expands and everything beyond a certain range is unrealistic. Well, I guess like if one of the galaxies are fixed and it's like expanding out, then as the universe expanding, the galaxies are kind of shifting. I don't know. Are the galaxies moving with this person?
The galaxies are fixed in our universe, and our universe is expanding. So imagine the surface of the Earth and all the cities on the surface of the Earth. And then there's some sort of demigod which is expanding the radius of the Earth. In that case, all the cities expand, look like they're expanding away from each other. If this demigod is able to expand the Earth faster than the speed of light, then the distance between 2 points that are far away ends up being faster than the speed of light. So you will never see those 2 different points. So it's the integrated effect of the expansion of the universe between us and a distant galaxy that makes it appear as if the universe is expanding faster than the speed of light. Now, I want to be clear, the universe is not expanding faster than the speed of light. It appears to be expanding faster than the speed of light. There's a weird coincidence in that the size of our universe, the observable size of the universe, is the same size as a black hole that has the same mass as the universe. And so that the edge of the universe is almost an event horizon. So we can't see beyond that event horizon at some level. So the universe doesn't have to be this way. If we didn't have dark energy, we would always see those galaxies. But the most distant galaxy, the other thing that happens is if they're very distant, is that the time also slows down, which I didn't talk about, time dilating. So when I see a star explode in the distant universe, it may take 2 weeks here in nearby universe. It may take a month or even a year to explode because time is moving really slowly towards the edge of the universe. So that galaxy never actually disappears from the universe. It actually freezes at the edge of the universe because time stops. Because the edge of the universe is just basically like the event horizon of the black hole. And that is another coincidence that has to get explained. Why is the mass of the universe give the size of the universe it's the same size as a black hole? It doesn't have to be that anything else. It's almost the same size. So why do you also explain that in the future?
So you're saying the inflation theory, how you're looking at positive factory place with the watching universes. If we were that they haven't found any statistical evidence of the universe. Yes. So why is that a leading theory?
Basically because a Nobel laureate thinks he sees it. So it's kind of hard to argue against it. When we do the statistics differently, we don't see it. But insofar as he sees it, and we can't really disprove the way he does it, it's still a viable theory. It's a really weird theory because it takes an infinite time and maps it into a finite time space. So there's this weird mathematical algorithm he invented, which is why he won the Nobel Prize actually, where he showed that black holes of any regular structures of any irregular size can collapse to a black hole. That is the same as his conformal theory. So the Nobel Prize he won is part of this theory, but it doesn't predict that cosmology is right. But the same mathematics shows that black holes can form out of anything. But unless we have better data, the problem is with that CMV, that's the only universe we have. It's not as if I can go out and observe another universe. There's no more detail that you can get out of that image. So it's kind of hard in the future to see how we're going to resolve this until someone convinces Roger that the statistics are wrong. We think he's wrong, in which case we discard that theory. But we don't discard black holes because the part of the math that's speaking of black holes is wrong.
You explained the whole thing about the ring thing in the Coulomb clock where you're talking about radiation.
Why they're circles?
Can you explain how they use it? How each one is
Because every point is the same age. So if at that universe, the universe is 380,000 years old. Right? So every point in that universe is 380,000 years. So every point in the universe, if you happen to be in that, you can only see out to 380,000 light years. Can't see any farther because the universe is older. So all spots have to have the same size, because that's the size of the observable universe that's set by the age of the universe in that early time. So each one of those spots is 380,000 light years essentially across, because that's the age of the universe. It's kind of a weird concept, but each one of those spots over time, the observable universe will get bigger and bigger. Those spots then begin to overlap. Early on in the universe, they can be separate.
So you're thinking that, good thing, sometimes you have to,
Yeah, I like the analogy of throwing sand into a pond. When sand hits the pond, each one of the rings doesn't touch the other rings. But over time, the rings expand and end up touching each other. But when they hit the pond, they're all roughly the same size. And that's the size of the ring depends on how old, how back in time you threw the sand. So every point in the universe, so if you look at this image where it is cold, is the red spots. That's where there's more mass. So that's where galaxies are going to form. If you happen to be in being able to live at that time, yeah, because it's 3,000 degrees. When you look out at the universe, you can only see 380,000 light years across. So therefore, that's the size of the observable universe. But because we live in a much later part of time of the universe, we can see these independent universes because we're looking backwards in time.
We have time for one more question, Dr. Suntzeff.
One way in the back. Yeah, go ahead.
Hi,
No, go ahead.
so you used the soap bubble analogy to explain how the universe is essentially connected to form that perfect circle. Looking at the artist rendition, if you have multiple soap bubbles that are stuck together, the intersection becomes distorted and then no longer perfect circles. Is it possible that that's happening with the universe as well, and that we have multiple universes that we're touching, so it no longer forms that perfect circle?
That's a good question. So early on in this universe, there are lots of quantum mechanics says that if you have one energy fluctuation, you have a spectrum of energy fluctuations. The question that therefore becomes how far separated are these fluctuations? The thing I didn't have time to go into because it's a whole other lecture is what the details of inflationary theory is. Inflationary theory posits that during inflation, the universe expands much faster than the speed of light. So even though 2 points may be next to each other, one point suddenly turns into a Big Bang universe. The universe is expanding really rapidly. This Fourier universe, the primitive universe, is expanding so rapidly that all these 2 points started out next to each other are now so far apart that they never see each other. So they expand faster than the speed of light. But it's still possible that some could touch each other. It's unlikely. And if they do touch each other, we would see this ring, and we'd be actually looking into another universe. We have no idea whether that universe has the same laws of physics as we do. If in these other universes, these parallel universes, some people call this parallel universes, but it's not like in string theory, which is completely different from what I'm talking about. So forget string theory, it doesn't work. It will work one day, maybe it doesn't work. So each one of these fluctuations ends up being pulled farther apart in the speed of light, so you never see them. But it's possible that in each universe there is a separate law of physics. Now, each one of these Big Bang universes is going to have a different age because they don't all happen at the same time. But if there are different laws of physics. Since I gave you that number, the 10 to 30, that is such a large number that if you have a large range in the laws of physics, and a large range of age, there are so many universes. There is one universe that looks just like our universe, that isn't our universe. And in that universe, everything is exactly the same except the addresses. Everything is possible except one detail is different. There are that many universes that you can fit that into. And that's why that number is so hard to comprehend. So many universes that everything is possible. Then it becomes a fine-tuning problem, then gets into theology. So thank you very much. Bye. I really like getting emails from anyone that wants to ask me questions about cosmology. So I'm really easy to find. There's no one else with this last name in the United States. So I'll go to Texas A&M and write my last name, or just go to Texas A&M and strongly to find my email address. Normally, after I give a lecture, roughly 10 students will start a conversation with me about questions you have in cosmology. And I would love to answer them because although most of you are not going to become astrophysicists, maybe I can still convince you, many of you will. I hope that I can stimulate your interest in the unsolved questions we have in cosmology. Thank you.
So that concludes the open house festivities for this evening. Thank you very much. Time for the early observing team to start heading up to Escorn. I'm gonna see what the weather's like. If you're potentially interested in going up for a quick tour of Escorn, just hang out here for a few minutes. I'll figure out what's going on. Eric, could you talk to me before you head out? Night, everyone.
Definitely.
See ya.
John Briggs might be showing up at Edstone with a photographer. It'll be very unobtrusive, but there's working on these beats with John, and then involves Edstone and telescope. Nothing with us. They might take pictures of you guys, but they will stay out of your way. Okay. And I'm thinking I might be up there with parents around 9:30. Okay.